Bruce Potter. Normally I start most of my talks with the same basic premise, which is you shouldn't believe anything. Really? Am I cutting out? We can hear you now.
Just really long. This is how we kill time, actually. There's like 10 slides, so I'm just going to talk. I paid him a lot of money to make sure the mics don't work. Normally I start most of my talks. I'll introduce Sasha here in a second. Actually just do it right now. This is Sasha Wood. She did the research with me as well. She's also with the KW Corporation. I normally start most of my talks the same way, which is you shouldn't believe anything I'm about to tell you. In general, I would encourage you to at least try to believe what I'm about to tell you, but take it with a grain of salt. This is based on research that we've done regarding entropy production and consumption that was funded by Whitewood Encryption Systems. So Whitewood's new company just came out of Stealth here today, actually, at Black Hat. They're in booth 967. They're focused on a number of things: quantum crypto, quantum random number generation, and entropy management. And as part of that work, they kind of had the question of how good and how bad is entropy management in the enterprise. So they funded us to actually go do some work to try to find the answer. So the work was led by Sasha and myself. Also, we had some interns who I'd like to acknowledge, Catherine Cleland from Lycoming College in Pennsylvania. Any Lycoming graduates here? It's not a particularly large organization. Let's see, we had Jeremy Renix from, where was Jeremy from? He was from the Penn College of Technology. Any PCT grads here? PCT is a wonderful institution where the security group is in the same college as the welding folks, and the dean is actually a master welder, like has a master's degree in welding. So it's actually a small college, but a good program based out of central Pennsylvania. And then Jeff Acquaviva, who has the greatest last name in the world. Jeff was a great guy. He's from Penn State. So we appreciate all the support we had from our interns as well. So again, I encourage you to stop by, learn more about entropy at our booth. But without further ado, talk about our research. So when we started this, we really wanted to just get an understanding of entropy in the enterprise. What produces it? There's lots of, I guess, kind of conventional wisdom, shaman knowledge about how is entropy generated, how is it consumed, and people kind of agreed tacitly, like this is how the kernel works and this is how OpenSSL works. But there wasn't a lot of hard data around it. It didn't appear people actually read the source code. There were some rants by Linus saying basically, let the real adults deal with this and you all don't pretend to be cryptographers, which I thought was a great Linus quote. Like that's typical Linus fashion, like I know it all and you don't know a damn thing, so shut up. That's his business card, actually. It's a slow joke day, I guess. We're gonna roll right into this. Jeez. It's also the widest room I've ever had to deal with, so I feel like I'm talking off the 50-yard line. We really wanted to look at also try to correlate random number generation versus entropy, because the two concepts, while tightly correlated, are not the same thing. So what we're going to cover today is all the findings from the research we had in this space, but the TLDR of the whole thing is no one really knows, or at least knew prior to what we did, what the hell's going on with respect to entropy in the enterprise. There was a lot of conventional wisdom that I think we've proven to be wrong, or at least highly suspect, and that's why I would say, please challenge this work, because when we saw things that didn't align with our worldview of how we thought random numbers and entropy were handled, we went back and reran tests and tried different hardware and kicked the interns around, you know, the beatings continued until morale improved kind of thing. And at the end of the day, this is our best results from those findings. So if you've got other data or you disagree, man, like throw the flag and let's have the conversation about it. First, the game. So which one of these use more entropy? So running LS or generating a 1024-bit RSA key. Any guesses? No, actually you're wrong, Simple. It is actually generating the Woohoo! The first one was not a trick question. I'm so proud of myself right now. How about generating a 4096-bit key versus a 1024-bit key? It is exactly the same. Good job. You get all the prizes we have up here. We have microphones to give away after the talk. So how about generating a 4096-bit key versus doing 4096-bit TLS with perfect forward secrecy?
So for those that don't know, perfect forward secrecy, effectively you're doing not just normal TLS stuff, but you're generating an ephemeral Diffie-Hellman key and doing all that kind of nonsense. So there's actually key generation involved in a PFS connection. As it turns out, generating the 4096-bit key, maybe unsurprisingly, uses more entropy. What about 1024-bit TLS with no perfect forward secrecy? So your standard issue, non-PCI compliant TLS connection. We can get into a PCI discussion later. Or 4096-bit, as it turns out, these are exactly the same. Same amount of entropy are used in both. And then, for the trick question, simple, BinLS, well, we'll get to that in a bit. That's the rest of the talk. Yeah. So here, in this case, as it turns out, when you run command lines, when you run any command from the Linux system, it actually uses a lot of entropy. And in most cases, running a command from the command line, like binls, bincat, bin anything, uses more entropy from the kernel than doing a TLS connection does. So when you think that you're getting all this high quality entropy to do some cryptographic operation when you connect to a web server, the administrator who types ls is actually pulling more entropy out of the kernel than you do when you perform the TLS connection. So we have data to back it up, so, you know, but wait, there's more. So with that,
is it my turn?
it is now your turn. I'm actually turning the mic over. For people that know, that's kind of a big deal. So.
So the thing is, there's many things complicated when you talk about entropy and randomness. There's sort of layers upon the layers. I'm going to begin with, and I'm going to get through them all. I'm going to get up to.
Can we get the mic on her now?
Is the mic guy over there? On me? Okay, so now I got a mic.
You got that mic.
Excellent. But how will you interrupt?
I will still find a way to interrupt. I promise you that.
So there's lots of layers when you have to think about entropy in a system. There's the entropy at the very bottom. There's randomness. There's what OpenSSL does with that randomness. There's what Apache or Nginx does with that randomness. I'm going to start at the bottom and work my way up. So entropy and randomness are different things. They're talked about as if they're the same thing pretty often, but randomness is about whether you can predict. Wait, now do I have two microphones?
Yeah, I think you do.
Now, randomness is about whether you can predict the outcome of a particular event. If I stand up here and I flip a coin, it ends up heads or tails with 50-50 odds because I do not have mad coin flipping skills. If Penn and Teller stand up here and flip a coin, it ends up heads or tails exactly as they decide. My coin flip is random, their coin flip is not random, but the only way you can tell the difference is that I am attesting to you that I don't know anything about flipping coins. Entropy is the notion of, if I take a bunch of coin flips and I put them all together, I don't know whether those coin flips are random or not, because you don't know if it's me or Penn and Teller who did it, but I get a string of zeros and ones, and I can look at that and I can say how much information is in that string of zeros and ones. And I can say that the, that the total, that you have 100% entropy if it looks like it came from a truly random sample. But you don't actually know whether it is truly random. You can't tell except for some kind of attestation at the beginning of that. Is it me? Is it Penn and Teller? Did I flip the coin so originally I generated the entropy just fine? Then I burned them on a CD and I used one for myself and I gave one to you. That data is going to look the same but is fundamentally different. The second one has no entropy because it's a copy of the first one. There are random number generators and pseudo-random number generators. Random number generators are now more commonly being called true random number generators. They use some underlying physical process, and I'm going to come to what that is to generate actual randomness, but there's still some kind of attestation that something in there is random. Pseudo-random number generators are deterministic. You put in some piece of randomness initially, and they spit out lots and lots and lots of data. Historically, these were kind of terrible, but now we have great cryptographic primitives, and so they are really excellent. You can initialize a pseudo-random number generator with 256 bits of entropy, and then you're allowed to run it for 2 to the 67 bits before you need to reseed, which is a lot of bits.
According to NIST, this isn't
According
like
to
our
NIST.
pulling that out of, if you look at NIST guidelines on how long you can allow a PRNG to run, assuming you seeded it appropriately, you get a lot of blocks, and some of these are actually requests, not just blocks. And some of the requests can be quite large, and so we're talking about very, 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 very large number of numbers that can be hauled out of a PRNG and considered to be still cryptographically safe from NIST perspective.
So a helpful analogy, perhaps, to think about it is if you imagine you have an enormous deck of cards, 2 to the 256, say, cards, that's more than the number of atoms in the universe, but let's pretend that. When you shuffle that deck of cards, that's what you are putting the entropy into the system, and then once you deal it, so that's your true random number generator, once you deal it, it's just your PRNG spitting out data. It's deterministic at that point. But the better the entropy that you put in, the better the random numbers you're going to get out of there. So here's how Linux sort of basically does stuff in a general sense.
So if I could interject,
Yes, please.
because that's what I do. There are very few comprehensive resources available, sans actually reading the code, to understand how Linux with OpenSSL and Apache, to take a particular use case, actually handle entropy and random number generation. So in order to haul this and later diagrams together, we've been reading the rand.c, which is effectively where the entropy sources are pulled from. We've been reading OpenSSL source code. We've been reading devrandom and urandom source code, Apache, modSSL, all kinds of things, as well as running experiments against that. So this is our understanding of entropy and random numbers and the ecosystem within Linux today. This does not necessarily marry up with what you would see on other websites and other documentation today. And that maybe is because the systems have changed over time, or maybe that people just had ideas of how it worked. And as it turns out, it doesn't work the way that they thought. So we're going to walk our way through this diagram over the next few slides so that you understand kind of discretely from a production to consumption perspective what actually is going on.
I think in fairness to the stuff you find online, people just change the code, right? And other people they don't update the documentation inside the code itself necessarily. And certainly the people who have written explanations of the code they're not being notified that that code has changed. So this is all being done on Linux 3.2. So Linux takes some data from basically interrupts. You move your mouse, you move your you type on your keyboard, you do some disk I/O, you get a network message, and it gets some entropy out of that. I'm going to discuss how it decides how much entropy it gets in a second. You could also have hardware random number generators that you plug into your computer. There are userland things you can run like Havage that will add entropy in. It gets all of these things. These things all they produce strings of zeros and ones with some kind of entropy estimate attached to them, and that gets stirred into the main entropy pool, which is that first thing right there. There are two PRNGs that take their seed data out of that main entropy pool. The one that feeds dev random and the one that feeds dev urandom. They're the same PRNG, different underlying data, but the same basic mechanism. And then you have applications that read from dev random or dev urandom, or you have OpenSSL that reads from mostly dev urandom in order to seed its own PRNG. And then you get your data all the way up, your random data all the way up into your application. So these are some software sources of entropy. These are very low production rate, and we're going to talk about that in a little bit. What the kernel does is it looks at these events and it says, how surprising is that event? Is it unusual that you typed left bracket? Is it unusual to have two packets that came together that close? And they hash some of that information together into their kernel entropy pool. Or you can have a wide variety of aftermarket hardware random number generators. So Ivy Bridge, in the new Ivy Bridge, well, they're not so new anymore, Ivy Bridge chips, there's a random number generator based on thermal noise that feeds into a pseudo-random number generator and spits out pseudo-random number data with a real good entropy source at the beginning as fast as you could possibly want it. There's Entropy Key, which is a little USB dongle that you can buy for $50 and shove into your computer. LavaRand actually will set up a camera looking at a lava lamp and use that to generate entropy.
Has anyone actually done that? I've seen a production setup of LavaRand. Like, people do that as a thing still. So you giggle, but there are people who care enough about entropy and don't believe these other sources, and they know they can audit their lava lamps and their cameras, and it's very important for them to be able to audit those things. And so the only failure scenario, the one that I'm aware of, is when the cleaning crew turned the lights off because they thought the lava lamp shouldn't all be on at once, and then it made a lot of zeros for a couple of days. So. But the PRNG caught it, right? So the PRNG is still, like, I got, to the 48 blocks I could give out before I worry, so it was just cruising right along. It is fairly amusing.
So here's a more in detail thing of this internal piece of the Linux kernel PRNG. I'm going to speed up because I know you're going to jump in a second, Bruce. You get the data in, it goes into this main entropy pool, it's fed out to the two PRNGs. The main entropy pool has a maximum amount of storage of 4,096 bits. In practice, we never see it get even close to that with normal software stuff because software produces entropy very slowly. You can increase the value, but it doesn't, since you never get up there, it doesn't really matter. You can increase the maximum available value. So you asked a question earlier about how were we figuring out how much entropy was being used. We were using this call into the system, this entropy avail call, which tells you how many bits are waiting in the main pool to be stirred into either of the two PRNGs. You have to be careful with that because of, it's on a later slide. Yeah. You have to be careful with that because of this thing where LS uses a whole bunch of randomness. So you can't actually just cat that file because every time you cat that file, you're going to use entropy just to run the cat process.
Yeah, if you want to, from a practical perspective, if you want to actually monitor available entropy, you should not write a script that does it, because every time you invoke that script, Linux will actually use entropy to run a process. And it cuts to the chase. What it does is that there's ASLR issues, there's other concerns when the copy process function within fork actually consumes a lot of entropy from the pool. And so when you go to check it, if you just like cat that thing in proc, like you'll actually cause it's like Schrodinger's cat. Like you kill the cat every single time, and you kill it by about 256 bits. So can you go back to the other previous slide? So you can write a program that will just constantly monitor it for you, so you're not actually invoking a new process. It's really the forking that causes the hit. Now, what's interesting here, and where I expect some people to start to disagree, so there are 3 separate entropy pools represented on this slide. Again, with kernel 3.2, we believe this to be true, and this kind of defies conventional wisdom. There is the primary pool that the kernel is maintaining at all times, and then there's a pool associated with dev random and dev urandom. And in general, the OS is keeping those close to 0, and when they need entropy, they'll reach to the primary pool and steal from that to feed their own PRNG. So the entropy estimation in the primary pool will be reduced, and the entropy estimation in the pool for dev random or urandom will be increased. And then the user or the application will pull out of one of those pools, and then it'll go back to the primary pool and pull down. And you can go read the code, and there are 3 separate PRNGs at 3 separate states and 3 separate pools all being tracked. Again, there's a lot of documentation out there that says there's 1 pool, or there's 2, one for dev random or urandom or whatever, but this is what we found to be true.
So here's some statistics looking at how much entropy is actually produced on VMs and on bare metal systems. When you look over these numbers, I have a summary slide on the next one. I'm not going to read through all these numbers. The numbers are really staggeringly low. An unloaded VM can produce about 2 bits of entropy per second. If I'm running Havage on a VM, I can get 12 bits of entropy per second. There's almost nothing in modern computing that runs at this low of a speed. I was actually looking at this before I came over here. New Horizons is out at Pluto, and it's sending back data. It's sending it back at 2,000 bits per second. So even these, it's just staggeringly low that this is what we're dealing with in a modern machine.
The average call into dev random or urandom for most of the code that we saw was asking for 32 bytes of random numbers, random data. And if you're asking for dev random, you're asking for 100% entropy when you do that. And so when you think about, on average, every time, again, if you spin up a process, it's looking for 256 bits, or 256 bits, 32 bytes of random number. The amount of entropy that's being poured into these pools is relatively small by comparison. And on a heavily loaded server, what we found is immense pressure on the entropy pools because the server is constantly asking more. But on even a moderately heavy loaded server, you're only adding on the order of 10 bits a second into the entropy pool.
So here's the summary, the interesting things from that previous slide. That a bare metal machine can make entropy slightly faster than an unloaded VM, but not a lot. That if you ping the machine 1,000 times a second, you get a lot of value for that on your VM, and even more on bare metal. Strangely, Havage makes that much worse. We replicated that, but we have no idea what's going on there. And then there's this weird result down there with RDRAND. So often you can't get through to RDRAND in the VM. The hypervisor has to expose RDRAND. So we didn't really look at it on the VM side. But if you have access to RDRAND on a bare metal machine, something goes wacky with the kernel entropy production. And we don't know if that is the kernel adjusting its estimates of how much entropy it's getting because RDRAND is being, we don't understand why that's happening. We would be interested to know.
So the kernel explicitly does not include data that comes from RDRAND to have any entropy in it. So you can feed in, so RDRAND, for those that have played around with it, can generate, hundreds of megabits of random data a second. And you can shovel all that right into the kernel, and the kernel can consume it. But at the end of the day, the kernel does not it does not increase the entropy estimation from that data. And as it turns out, it's because of Snowden, right? Like people started to think that somebody had backdoored RDRAND, and therefore somehow you could then learn the state of every Linux box in the world and all the PRNGs, and therefore, at one point RDRAND was the source of random numbers, random data and entropy going into the kernel entropy pool, and then it was totally removed, and now it's in there in 3.2, but it doesn't increase the entropy estimation. And then in that whole process, somehow the entropy estimation that the kernel provides ends up being even worse than if you didn't have RDRAND connected. So this is the point at which you should challenge. I don't know if the kernel's entropy estimation discussion or algorithm is correct. Right? We didn't go down to verify the appropriateness of that. There's been studies around this polynomial analysis that does to see how surprising, like I really want to see a surprise kernel, like, wow, that was an amazing packet. Like, and then the board kernel, like, I saw that one already, guys. There have been some critical analysis of that surprising algorithm, but I don't think that there's been any kind of conclusion drawn from it. And I think in general, people have felt like, meh, it's good enough. So we went with a, meh, it's good enough. This is what it spits out.
I think that whenever anybody has to make a decision about kernel entropy estimation, they always choose the most conservative route. And so they're sort of going along with that, with the RDRAND decision as well.
And we should note also with the bare metal, the virtual machine versus bare metal, there was a lot of, bare metal generates so much more entropy than VMs, and VMs are starved. Well, they both kind of suck. But in network cases, I think probably because of how it's handling the network packet at the hardware level, we did see at least about an order increase in how much entropy you got from heavy network load. But still, it's on the order of tens of bits a second. It's still not very fast.
We also looked at various Android devices, seeing how much they have. They actually do much better, but still in the tens of bits per second, 20 to 40 bits per second of entropy. We thought, when you imagine I have a cell phone in my pocket, surely the accelerometer is generating information all the time. Surely we could just use that. Doesn't seem to be connected into the entropy system at all on a cell phone, even though it would be, we believe, a pretty excellent source of entropy.
Yeah, it was actually fairly amusing, right? Here, shake this phone, run it for 5 minutes. Because that's how long our tests were, and so, hands it to his kid, and the kid runs around with it and shakes his phone.
So here's how dev random and dev random work in the Linux 3.2 kernel today based on what we've seen up there. Dev random provides output that, if you get output from dev random, there's roughly 1 bit of entropy going into the PRNG and for every 1 bit of output that you get out of the PRNG. Every time, the way it works is these are the old version of the slides.
Oh, I'm sorry. Well, I can do an interpretive dance for the new version if you like.
I'll wing it.
Okay, excellent. Winging has started.
So the way the dev random PRNG works is that you ask for 64 bits. It's the smallest you're allowed to ask for because you run a 64-bit machine. It goes and it checks if there's 64 bits of available entropy in that main pool, and if it is, it sucks them out. It hashes it in, it gives you your 64 bits, and then it takes a hash of that and hashes it into its own pool. If there's not 64 bits of entropy in the main pool over there, then dev random will block until there is. And as we've seen, that you're going to be sitting there for 30 seconds while it tries to build itself up. Dev random works a little bit differently. You ask for 64 bits, it checks to see if there's 192 bits of randomness, of entropy in the main pool. If there is, it hashes that in and it does its little dance, it passes it out, it hashes its output back into itself. If there's not, it just says, meh, and it gives you some output and hashes that output back into itself. So this is why dev-urandom never blocks. If there is entropy available in the main pool, it will draw from it, but if there's not, it just does not care. There's one other way to access these pools, and that's get random bytes. It's a kernel call, so that if you're inside the kernel, you don't actually have to call out to user space and the character devices. But it draws from the non-blocking pool, which is contrary to some of the documentation out there.
So get random bytes is quite literally just a wrapper for dev-urandom. I mean, you can look at the code, it's very simple, and it's just a wrapper to get to the same functionality that urandom exposes. So what we see here is dev-random. If you pull from dev-random, you can just cat dev-random, right? Cat dev-random, and watch stuff go to the screen. And then if you query for available entropy, you'll see it just goes to 0, and then every once in a while you get a little blip and it'll barf out 64 bits as it hits that ceiling. Dev-urandom has a 128-bit floor. So if you cat dev-urandom, you'll see the kernel estimation, entropy estimation drop to 128 bits and then sit there. It'll never haul that last 128 bits out. The kernel doesn't let it tap into that last 64 bytes. So it's interesting to watch, and again, it's kind of, there's no documentation that says that it does this, but this is what we saw through our experiments over and over and over, is this 128-bit floor that dev-urandom enforces.
So here are some things that are not random.
Just so you're not confused.
So RAND, which is a C function, has been around since the 60s. RAND uses a very, very old kind of linear random number generator called a linear congruential generator. Do not use RAND. I don't know, if you have a button and you're like, maybe it should be red, green, or blue, RAND is fine for that. But do not use it for scientific data. Do not use it for Monte Carlo simulations. Please, please, please do not use it for cryptographic data, because if you can get 2 samples out of a linear congruential generator, you can get the internal state of that generator, and then you know all the bits going forward and all the bits going backwards.
That's bad.
Not very secure for you. And it didn't matter in the 60s, right? Because, I mean, RSA and Diffie-Hellman weren't invented until the 70s, at least on the outside. So there are better pseudo-random number generators. Python uses Mersenne twisters, C++ uses Mersenne twisters. These are better because you need 650 outputs in order to back engineer the internal state of the thing. You should seed these well. Seed these with something from dev-urandom, but you should also add more seeding into it every 600 calls so that people can't get into the internal state.
So this is the part where we admit that a lot of our initial testing was just kind of flawed, because one day we're sitting around with our interns and we're running some tests, and I run a series of commands and I cat entropy avail, and I had some number, and then I cat entropy avail again, and it's a shorter number, and then again, and it was an even smaller number, and the box is unloaded, nothing's happening, and I'm like, what in the living hell is going on here? And so go to the next slide. And this is, it turns out, where we found out that when Linux spawns processes, there's a whole bunch of things it does to try to protect you, try to protect memory, try to mask itself from all kinds of different attacks, and it ends up asking for 32 bytes of random number off of dev-urandom, and if it's there, it'll decrement the entropy pool by a lot, 256 bits. So at the end of the day, when you're on a workstation just catting entropy avail, you're putting a huge dent into the kernel entropy pool without even realizing it. And that's where we get into this whole, like, hey, these commands actually take more entropy than OpenSSL. So we're about to get into the OpenSSL stuff that we found out. And in general, the kernel is very good about snagging entropy when it needs it, and some of these cryptographic functions that you would think would be very good at it are not. It's interesting, I should say, that we validated that on a number of systems. Some systems didn't demonstrate the same level of aggressiveness to tap the pool as others, and we couldn't find a common thread, so there's still work to be done there. And if anyone goes and plays with this later and lets us know like why we saw that some places and not others, we read a lot of code. I'm not allowed to write code anymore. They've taken my compiler from me, but I am allowed to read it. And we've read a lot of code, and we can't really get to ground truth on what's going on there.
One of the interesting things about this is that this address relocation, the randomness that you need from that is being pulled from the highest cryptographically best randomness out of the system that it has available as an unrestrained resource. It's not, I don't know, does address relocation need to be that complicated?
Well,
that secure?
You got to keep the hackers away. It's kind of a joke. I mean, it's interesting because like bin ls, I mean, it's not like bin ls is, this relocation is that big of a deal. But there's all kinds of things that happen, even the kernel comparison stuff that occurs. They try to blind processors from each other so they can't kind of introspect on each other's memory space. And so there's even like an abstraction that occurs in the KMCP stuff. And so it's taking all that information to basically make each process more secure and discrete from each other.
So now we're going to talk about how OpenSSL does it. OpenSSL runs its own PRNG outside of the thing from the kernel. It uses devu random to seed that, and then it uses that same PRNG for all cryptographic operations, long-term keys, nonces, ephemeral keys, everything. The kernel knows nothing about what's going on in the OpenSSL PRNG after it has been initially seeded. OpenSSL only seeds once per runtime, once per, let's say, process. So this is, if you're generating long-term keys and you do it at the command line, OpenSSL gen RSA 1024, everything's fine because you've seeded it well and now you're off to the races. But if you're using OpenSSL as a library under Apache, what you're going to see is that that gets seeded when the process is initially started. So if you fork, you'll get a reseed. The forking happens earlier. But if you fork, you'll get a reseed, but you're going to use that same thing for as long as that Apache process is running. Our data shows that an Apache perfect forward secrecy connection uses about 500 bytes of random numbers every time you set up an SSL connection. And so all of those are going to come out of the same PRNG, seeded with the same 256 bits.
So you can put, for those of you that have administered web servers, you can put limits on Apache to say you can only handle so many children per Apache server just in case there's a memory leak or something, and it'll shut it down and spawn a new process. Apache, I think last time I checked, by default does not have a limit. I mean, it's a normal thing you would do to tune for high performance situations, but not something people would do on average. But Apache could technically just run forever with that one seed that you gave it when it started, and that's it. The code off on the left there, if you want to go track that down in OpenSSL, it gets initialized once and only one time, and it never goes back through that chunk of code ever again. I mean, we've instrumented that. That happens one time only for Apache with mod SSL and every other thing that OpenSSL does by natively.
So and there's no reason for this. OpenSSL knows how many requests have been made against it. It could be tracking and reseeding from devu random, from good cryptographic data, but it just does not. The second issue with OpenSSL is that when it pulls its data from devu random, it actually has no knowledge of how good that seed is. When you first start up a machine, or if you copy a VM or you clone a VM from another one, they'll have identical randomness initially, and OpenSSL has no way of knowing that or doing anything about that. In Linux. FreeBSD is a little different. They're a little smarter, actually. FreeBSD doesn't have a devu random. It only has a dev random. And it might not help with the cloning of a VM problem, but it will block until it gets seeded correctly initially, and then it will run free after that.
Yeah, I mean, the way to think about this is you can conceptualize a world in which OpenSSL would look at the kernel entropy pool and say, is there at least 256 bits of entropy in the pool that I'm going to make a call and get it, right? Ignoring any talk-to issues or whatever. Like, it could do this in some sane fashion, and then it could pull the entropy and then verify, did I get high-quality entropy out of the kernel? Yes, no. Because you don't want it to block necessarily on dev random, so you're going to do this on urandom. Like, you could envision that code, right? It doesn't exist. OpenSSL is just like, get data from devu random, 32 bytes. Okay, good. Whoop, it just keeps cruising. Whether or not it was high quality, if the kernel was under heavy entropy pressure, no clue. It just takes it and runs. So you would, again, I think, conceptually expect a little better out of OpenSSL, but it just does not care.
So Apache interfaces to OpenSSL through its mod SSL module. Apache initializes the OpenSSL library when it first loads up, and then it later attempts to add entropy to the OpenSSL PRNG. Unfortunately, its efforts to add entropy are not very sophisticated. Did I just go off mic?
Yep.
Am I actually talking?
Yeah, no, you're off mic now. I'm off mic too. Excellent. This is entropy. We've generated like 8 bits of entropy so far in this talk with a lack of microphones. We've exhausted the entropy pool until you all need to stand up and just move around a lot, and that'll get the microphones working again.
I'll yell this because I'm a little louder than you, if that's okay.
Okay, go for it.
Okay, I will go for it. So mod SSL will attempt to, it does not ever reseed. On the previous slide, we had a thing where there is a way that you can reseed OpenSSL. Like you can call like rand poll and seed it yourself and everything will work fine. But at the end of the day, they don't do it. Instead, what mod SSL says, I'm just going to invent my own way of reseeding the PRNG, and it does three things. One, it takes a date and time at a 4-byte resolution, which turns out is not a high-resolution timer. That's pretty low and is somewhat predictable. The PID, which is generally static for most things like web servers. You don't get like massive PID changes all the time. The PID's pretty constant. And then it does this trick where it takes 256 bytes off the stack and just tries to read it. So it makes like a random, we'll get in the next slide, it just says, oh, there's a bunch of data here, it probably changes. So, hey, he left the room and it works. That's weird. We're good now. It was just, I think that the board was sick of you, man. It's like, get out of here. And this 256 bytes that comes off the stack, it's pretty much just said, like in the mod SSL documentation, like, oh, we just declare this array and then we just read it a lot and we think it changes. So we don't think it changes a lot. They initialize this array. And then
They don't initialize the array.
no, they don't initialize it. They declare it, and then they're like, yeah, there's this thing, and then they just read it. We ran a run for a while, 600,000 requests with just about 4,500 unique values. So it varied less than 1% of the time that we queried it. So you've got this source of entropy being fed into mod SSL. Now, give them credit. This is every time you make a request, but the amount of entropy, the amount of kind of like surprising things here is very small because the date at a 4-byte timer changes pretty slowly. The PID doesn't change at all, and then this big stack frame that they're reading doesn't really change much at all either. So it's better than nothing, but it's a very complicated system to basically maybe get a bit or two in the process.
So Nginx is the next most common Linux web server out there. Nginx actually just doesn't even do as well as Apache. It just uses the OpenSSL random number generator, and then that's the end of that. Never reseeds it after startup.
And the Nginx developers in their wiki make some claim like, yeah, we could do that, probably should. Like, okay, like good talk. I'm glad we've done that.
Do you want to take back over?
Yeah, I guess I'll stand up now. I've been kind of silent, so. Sasha's very good to put up with me. So now we wanted to look at and see, we mentioned like, okay, so we've been talking about entropy, and the entropy estimation within the kernel. So how many random bytes, how much random data is actually consumed when you do kind of basic things like generate keys and visit a web page and that kind of thing. So, I mean, the data here is largely unsurprising. Again, we're assuming when we do all these things that OpenSSL was seeded with high quality entropy, right? Like it wasn't just something that's been stirred in already and we've seen, and the kernel didn't give it really good random numbers, but OpenSSL has no way of knowing, so it just kind of guesses, says everything's okay. So obviously it unsurprisingly takes a lot more random bytes for OpenSSL to generate a 4096-bit key than generating a 1024-bit key. For the Apache, again,
Can I just say what it's doing there? So to generate a 4096-bit key, it needs to find a 4096-bit prime. So it picks a number, it checks whether it's prime, and if it's not prime, it adds 2, and then it checks that, and it keeps going until it finds one that is prime. So the 4096 bits, the initial generation, is not a lot of data. The extra primality extra random numbers are coming in the primality test. They use a probabilistic primality test, and so they need a lot of numbers to attest that a number is prime. So you might get lucky and find a prime early on, or you might have to go really far to find a prime.
So the question here is, how much entropy do you really need in order to be secure? So it's interesting because you have to think about the types of attacks that PRNGs are likely to come under. And one is control of the entropy spaces, entropy sources, right? This is the fear that RD RAND has been backdoored. And then somehow someone is barfing out a preset data at 400 megabits a second or something like that. And I have control of your mouse and I control all these other things. And therefore I know all the inputs so I can know the state. The second attack is I just know the internal state of your PRNG. And so since I know the internal state, I can know all possible forward states at the very least. It's a hash, so maybe I can't go backwards, but I can at least go forward. And the other one is, hey, your PRG kind of sucks, and I can just observe the traffic and figure out weaknesses and that kind of thing. Controlling inputs, by default, there's a bunch of different sources of inputs, and it's difficult to control all of them. And in general, for most PRNGs, once they hit that 256-bit of entropy mark, once they get 32 bits of entropy, they tend to perform pretty well. NIST has made this claim. Other researchers have made this claim. We didn't go and analyze the PRNGs. That was a little out of scope for what we were trying to accomplish. But at the end of the day, if you can hit that threshold of actually having 256 bits of entropy, things that you did surprising things to feed your PRNG, you're probably going to be okay. And even in the case of most obscene adversary, it's very hard to control all those inputs. Knowledge of the state. So if there's one takeaway here, like the internal state of the Linux kernel when all this is going on is complex. It's fairly difficult to know the state, and even what we found is observing the state gets like a Schrodinger state. It can be, can perturb it, so it's difficult to figure out exactly what's going on. There's probably race conditions in there, like if you really tried to haul this thing apart and then know the entire state and then know all states forward, it may be very hard to get that snapshot. And observing the output, again, according to NIST, it's a lot of blocks that you need to observe. Now, the caveat to all this is, as it turns out, cryptography relies on things being done correctly, right? And we can make a lot of claims about how good these PRNGs are, but the PRNGs, when they've been analyzed, the claims are made based on being seeded correctly, right? And what we found is, in a lot of cases, it's not seeded correctly. So what the actual applied impact of this is, we're not really sure right now. But what we are sure is, I'd say 9 times out of 10, you're not seeding the way that you think you're seeding. You're not getting the high quality entropy in the front end, and so the cryptographic impact on the backside is unknown. That scares us from a cryptography perspective, because when there's unknowns in crypto, eventually things go sideways. So we're hoping to shed some light on this in order to get people to care about this and address the concerns. One of the things that we've done also is created a client that you can use today. You can download it and try to address some of these issues rather than waiting for the Linux kernel to be fixed and that kind of thing. So what this client does is it actually sits inside of OpenSSL and replaces the random number generation engine. We saw OpenSSL is not necessarily making good decisions, but we horseshoed in good decisions on its behalf. So with this library, you can select what entropy sources are used. You don't have to mess around with the kernel. You can choose how to seed them, which PRNG you want to use. You can how often you want to reseed it, all kinds of things like that. You can get local, you can get network, you can get all kinds of different sources of entropy to feed into this thing. And so we get past all the kernel nonsense, all the other stuff, and just replace whole hog what's happening inside of OpenSSL. Now, you would ask, why would we do that? Maybe we could just do a kernel patch or something like that. Why could you just go with the status quo? Well, right now, the status quo is, it's all kind of broken. Nobody seems to understand it, so we figured we'd just fix it ourselves. EDG and Havage, I can never pronounce it, had weird results for us. So these userland entropy daemons, I don't know how many of you were sysadmins back in the 90s, but you can, if you're old, you can raise your hand. I did not mean to call you old, I'm sorry. Woo! That was the first thing you did, right? You had to install a userland entropy daemon before you fired up SSH so that SSH could generate reasonable keys, because the source of entropy were so bad. And there's a lot of userland entropy daemon stuff that still occurs, but from our analysis, sometimes it's not as good even as just leaving the system alone. And so, like I said, we decided just to pumpkin scoop out what's there in OpenSSL and replace it with our own. Now, a quote from the Linux kernel mailing list, not a quote, but a bit of history. So in 2011, Matt Mackel basically said, hey, if you got RDRAND, if you're on an Ivy Bridge chip, use RDRAND as the sole source of entropy because it's wicked fast and wicked good. And then Snowden happened, and well, actually, I guess Theodore So took over the kernel, and he added the other sources back, said that's kind of psychotic. You don't want to put all your eggs in one basket. Then Snowden happened. Then there was a battle to remove RDRAND altogether, and then Linus just uncorked it, where he basically said, let adults do what they're supposed to do and don't pretend to be cryptographers anymore. Its short answer, we actually know what we are doing, you don't. Now, what we saw is when you turn on RDRAN in Linux, you get the worst entropy estimation of any other way that we had to put entropy into that system. So with respect to Linus claiming he knows what he's doing and we don't, I will challenge that. I don't believe that to be true. And that, again, is terrifying, right? Because he's like the arbiter of what the hell goes on in all these servers, and he makes the decision. So I don't think he knows, and because of that, we went up the stack and we went into OpenSSL land. So effectively, there's two components of the library. There's a daemon itself that can hook into whatever source of entropy, local and remote, that you want to feed it. And then there's the library that gets installed into, that replaces part of the OpenSSL source code. So OpenSSL has a configuration file where you can specify the engines that you want to use. And if you just run OpenSSL, you can just change the configuration to point at our library, and it works great. This is all in the README, by the way, what I'm telling you. But it's interesting because not anything, but most things that call OpenSSL don't read OpenSSL's configuration. They just use the default. So if you like hack together OpenSSL and have like an OpenSSL configuration, ModSSL and Nginx do not care about that thing. They will just use OpenSSL in its default trim. So you actually have to then go back and, I guess, recompile ModSSL or Nginx if you want to use our library and use Entropy through that. So once it's installed, there's an eye chart here. We didn't want to do a live demo and taunt the demo gnomes, but once you get it installed, it is identical in process. It's just OpenSSL as you know it today. You can generate keys, you can generate certificates, you can check on the status. It'll actually barf out extra information to say, hey, here's what the entropy situation looks like, so that you can validate it and say, yeah, it looks like it was in a good state when I generated this certificate or this key, and then continue on. That's not something you get today, right? OpenSSL is just like, here's your key. You're like, boy, I hope it wasn't all ones that went into that thing. So it works very seamlessly. It's very transparent once you get it installed. And like I said, it just gets out of that whole universe of Linus and the kernel and everything else that's going on. So it's currently available on whitewoodincryption.com. We're actively developing the client still. We're looking to integrate it with other components and integrate it with other sorts of entropy like Whitewood's QRNG and other entropy offerings that are out there, and also increase the stability and things of that nature. I won't necessarily make a lot of claims about the stability. We've tested it. We smoked it out pretty good. If you download it, if you break it, let us know. We would love to make it better. We'd love to get feedback on this. I think this seemed like an interesting idea when we started it, and as we got into it, it got scary. We realized how few people really understood what was going on when it came to seeding these RNGs and what was happening with the entropy pool and the kernel. So I think we've taken this on as a bit more of a holy war than we had in the beginning. So we're pretty passionate about it. So if you have feedback, we'd love to hear it. So with that, I'll take a few minutes for questions. There's like mics if you want to be heard. He's like, no.
Can you tell me a little bit more about your QRNG?
We can tell you more. I don't want to turn this into too much of a product pitch, but there's a QRNG at the Whitewood booth that you can stop by and take a look at. Sasha?
Q stands for quantum, right?
Quantum, yes, it is a quantum. It's not like Q like the guy from James Bond. So it's a quantum RNG. It's a PCIe card that produces high quality entropy from a quantum source that's on there.
At 200 megabits per second.
200 megabits per second. So, other questions?
Yeah, I was just curious if you'd done any kind of analysis on like NSS or mod NSS, like to see if it's any better.
No, we didn't look at NSS or mod NSS at all.
So you guys looked at the entropy pooling for ModSSL, Nginx, and OpenSSL. Did you guys look at the boot up process for the kernel and see what the entropy pool was doing during the boot up?
I mean, we didn't explicitly look at it. I mean, there's state that's saved and then brought back to life through that process. But
At startup, it actually saves us some entropy as it's starting things up and writes it to disk. And on the next startup, it will use that to seed its entropy pool the next time. So this is a little funny. It would make more sense to write that little piece of entropy to disk at the end, but if you crash, then you wouldn't have that entropy there for startup. We know that some stuff is seeded in, is forced into that as the machine comes up, because if you have two identical VM images and you start them up and you have them generate SSH keys, they're different, but they might not be very different, as we know from some other research where they found that there were duplications in RSA keys and shared factors across the internet.
Is the client only a hardware solution? The client is, right, it's open source and it's software and it runs and it can hook into any entropy source. The quantum random number generator is a hardware solution, but everything that we've shown here is all software and it's all open source. So in a headless machine, you know, if you just use the default entropy sources, you're going to be kind of prey to the same problems that we have today, except for the fact that we'll constantly reseed. Right, so right now, if you're running in a daemon, it will never reseed in any meaningful way. You know, we will constantly reseed. So even if it starts out somewhat suspect because you have limited entropy locally, over time it will increase and increase and be better and better and better versus what happens now, which is just you take what you had at the beginning and you run with it forever.
Bruce,
Yeah.
question for you. Have you or any of your organization submitted a contribution to OpenSSL to reseed after X number of blocks? Sasha was saying that it keeps track of the number of blocks that are requested. Has any contribution been made to correct that problem in OpenSSL?
No, nothing's been made, and this has been, in some circles, kind of mumbled about for a bit. There's been discussion on how to make this better. I think what we're hoping to do is build enough support to get it changed. I think this is an area where, I guess to be polite, there's a lot of concern of rocking the boat because some of this code is ancient. If you look at even like
And fragile.
fragile as all get out. So we are open to talk to folks that are working on OpenSSL to make this better, but we have not actively engaged the team at all. The closest thing you'll see to O-Day at Black Hat.
Could you speculate or give us reasons why you found Android had a higher rate of entropy generation than a heavy loaded server?
Yeah, that's a great. So that one was completely surprising to everyone because, you know, I don't know, there was a Bitcoin hack recently where like a wallet got owned because like developers didn't like seed the wallet properly with entropy and like a whole bunch of keys got generated the same and you could steal a bunch of crap. And the comment was made like, wow, you know, Android is horrible at generating entropy. And we're like, well, it must be just junk. And then we fired it up and it was like an order better than, you know, a Linux server. What the hell? Like we didn't have time to really dive in. I mean, the core code is the same, and my guess is at the underlying thing that whatever the hell's happening in the cellular network is probably really surprising and really helping things out. So versus an Ethernet network, which is probably a lot less surprising in a lot of ways. If I were to even begin conjecture, I would say it's all due to cellular radio. It's not due to the accelerometer. That was the one thing we verified. So we got one guy with a mic, and then we'll get to you.
Have you had any speculation as to kind of attacks that could be modeled based on these flaws? For example, if you were to exhaust the entropy pool while it's blocking, slipping something in that isn't truly random or a DOS condition, have you thought about any of that kind of stuff, the after effects of what your research has found?
So, I mean, it's tough. Like I said, you know, this would be about controlling the input state or knowing the input state. And if you're using a reasonably good PRNG, like it's still a hard nut to crack. It starts to weaken basically the core of what you believe in when you're generating key material and things of that nature. It would have to be something that would fall in line in that front. We didn't see anything that directly led to a compromise, but again, we're looking at least with OpenSSL, we're looking at heavyweight, well-reviewed algorithms that people are pretty familiar with. And if other people are using this as a roadmap and engaging other algorithms, like they may be totally broken and sideways, but these ones here are relatively resilient to those types of attacks. So, simple. You want to use the mic? No. Okay. Did we code? Or we commented our code and stuff?
We did comment our
yeah,
code.
there's readmes and comments and everything. There was interns who were horsewhipped.
We did comment our code.
Yeah, there's readmes and comments and everything. There was interns who were horsewhipped. 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 There was interns who w Yeah, I mean, we try to make this something that's, the question is the client, I guess to paraphrase, not crap, is probably what Simple's trying to say. No, I think it's pretty robust, it's well documented, there's readmes, all the code's well commented, I think it's well structured. It's actually pretty easy to read, and like I said, I'm actually pretty lousy with code, so our intent is that people can pick this up, use it, and extend it, and do something productive with it, so.
So
One last one, I think.
there's a number of
Yeah.
test suites. Sorry, there's a number of test suites out there for measuring entropy. You know, BSI runs their test suites, or you can run NIST on measuring randomness. But you guys are actually kind of using random data to generate an entropy pool, so it's kind of inverted. Did you actually do any validation on what your output is by running BSI or NIST?
So those kinds of tests, the entropy tests are designed to be run on true random data.
Right, and you
one of
guys
the
can't
things
get at it.
That's a huge problem with those is that if you take just garbage, a string of zeros, and you put it through a PRNG, you're going to get out data that will absolutely pass those entropy tests.
Correct.
Because the PRNGs are so good. So anything that comes out of the PRNG, you have to validate it by looking at, it's this attestation. Where did this data come from back in the beginning? Because as soon as it goes through any kind of modern cryptographic primitive, you can't tell whether it's good or not anymore.
Well, no, I mean, that's what the NIST tests are for. BSI is for testing entropy. The NIST tests are for actually testing randomness.
Which you're talking about? 90B. No, 90B.
Yeah.
90B is for testing entropy. NIST has other tests. Maybe we should talk about this after?
All right.
All right, well, I think that's it. It's been fun. Hope you enjoy your lunch. Thanks very much.